Hello guys, this is a video on how to deal with cross-sections in calculus. To start this off, I've drawn a few figures with cross-sections whose areas equal a of x or a of y depending on the graph. A of x and a of y represent the cross-sectional areas of the region they're referring to. In the cylinder diagram, for example, the area of a circle is pi times the radius squared, and because the slices of the shape are circles, their areas are pi r squared. Now, as you've learned previously, for these shapes with a cross-section whose area is a of x, the volume can be expressed as such the integral of a of x dx from a to b. The same thing can be said for a of y. However, cross-sectional problems will often tell you what axis the cross-section is perpendicular to. Be sure that when you do these problems, you understand that the formula for cross-sectional volume is in terms of x when the cross-section is perpendicular to the x-axis, and that it's in terms of y when perpendicular to the y-axis. Forgetting to solve in terms of the correct variable is a common mistake when it comes to cross-sectional problems. Now that we are familiar with the formula for cross-sections, let's try out a few problems. The bounds of region B are the x-axis, x equals 9, and y equals root x. Bases of cross-sections are perpendicular to the x-axis. And last, each slice of region B is square-shaped. The first step is to cross-section questions is drawing out a diagram. This curve here represents the equation y equals root x, and here we have x equals 9 and a line that cuts along the x-axis. This region is shaped with the bounds I just covered. Now, as I said before, each slice of this region is square-shaped, which means that if we were to take this region and slice it up, each slice would look like a square. This whole thing reminds me of slices of a loaf of bread. We look at one slice and find its area, which is base times height, or s squared, since the slice is a square with equilateral sides. We can use s squared, the area of the square slice, to get the volume, aka the integral of a of x from a to b of the region. In this case, we'd go from 0 to 9. And finally, we can substitute root x in as s for this equation right here. Why did I change s to root x? We'll take a look at the graph. The area as well as the volume of the region is changing as we move to the right. The region is ultimately getting bigger because the function y equals root x is kind of stretching out as its x values get larger. Since that function is changing the side values of the square slices, we can substitute it in as s. We then solve to get 81 over 2. A common mistake in this problem would be to include pi as part of the volume formula. Since we're dealing with squares, and because they're cross-section problems, the volume formulas don't include pi in them. Next is to find the volume of a pyramid with a square base, length L sides, and a height of h. Now, why does this problem seem familiar? Well, it's because if we draw it out, the shape is the same as the one from the first page I was on. Here's another diagram I drew of this problem in case 3D diagrams aren't your style. Each slice of this figure would also be in the shape of a square, just like the last one, except we're dealing with a different shape and the problem's in terms of y. If we look at the pyramid directly from the front, we'll see that we have two similar triangles, and we know that the ratio of any two sides of similar triangles must be equal. So therefore, s over L equals y over h, meaning s equals L over h times y. So, the cross-sectional area is s squared. We're dealing with squares, aka L squared over h squared times y squared. Since we're observing the volume in terms of y, our bounds are also in terms of y. We go from 0 to h, the height, for this volume. And when we solve, we get 1/3 L squared times h. One more problem, guys, and this one's harder. We have to find the volume of a torus with radii little r and big R. One of the hardest parts of this problem is seeing what the cross-sectional area needs to be. One of them is definitely the circle of radius r that we're rotating about the y-axis as the cross-section. But how do we set up an integral using this? What we'll do is use a cross-section shown in blue. Let's cut the torus perpendicular to the y-axis to get a cross-section of a ring shape. That's all been said and done in these two figures, the left one, which represents a full cross-section sketch, and the right one, which is a more important sketch of the circle being rotated about the y-axis. You would think that with all these drawings we were in art instead of calculus. By looking at these diagrams, we can see that the equation for this problem is parentheses x minus big R squared plus y squared equals the radius squared. For the inner radius is x equals big R minus the square root of little r squared minus y squared, in the outside radius is the same thing but plus. We know that the area of something of a ring shape would be the following, so we just plug in our inner and outer radius values to get the simplified area, which is 4 pi times big radius times root small radius squared minus y squared. We also know our limits, negative little r to positive little r, because the lowest cross-section occurs at negative little r, and the highest is at positive little r. We plug in our boundaries and the area in terms of y to get 8 pi times big R times the integral of root little r squared minus y squared in terms of y from 0 to little r. That's a mouthful, but we're not done. We've now reached the second really tricky part of this example. Let's suppose we wanted to use an integral to determine the area under the portion of the circle of radius r and centered at the origin that is in the first quadrant. We know that the equation of the circle is x squared plus y squared equals r squared, and that if we solve for x, the equation of the circle in that first quadrant is x equals root r squared minus y squared. If we want an integral for the area in the first quadrant, we can think of this area as the region between the curve x equals root r squared minus y squared, and the y-axis for y goes from 0 to r. And this is a equals root r squared minus y squared dy from 0 to r. Because this integral represents 1/4 of the area of a circle of radius r, we can say that that area equals 1/4 pi r squared. So, putting all this together, the volume of the torus is then 2 pi squared times big radius times little radius squared. Thank you for watching my video, and I hope you enjoyed.